Hello and welcome to our fourth lecture where we're going to continue discussing motion in one and two dimensions. As a review, last time we introduced this idea of projectile motion where we can think of it in the same sense as free fall, as in there is only acceleration due to gravity, and in the horizontal direction there is no acceleration, there's constant velocity. And this kind of motion is characterized in the absence of air resistance as a parabolic trajectory. We also looked at our equations of motion and how those would change in the special case of free fall, where I have no acceleration in the x direction, but I have the acceleration due to gravity in the y direction. And then we applied those equations of motion to an example of a person jumping off of a cliff into the water, and we were to solve for how far horizontally this person lands compared to the base of the cliff. What we found out was that we needed not just one equation to solve this problem, but we needed to use two equations in conjunction with one another. The first equation that we used was the equation in the y direction for position. And in using that equation, what we did was solve for the time. And then we plugged the time into the equation for the horizontal direction in order to find this displacement horizontally. Okay, and in the end, we made sure to fact check or sensibility check our answer, which turned out to be around 8 meters, and we agreed that that would be a sensible distance from the base of the cliff. Okay, so another fun application of this idea of projectile motion is to see what happens during a game of baseball. The flight of the baseball is often, there's a lot of physics involved there, and you can actually go to this YouTube link if you want to look at all the details about that. We're going to satisfy ourselves with just one example related to baseball. But before I get into that, I want to introduce yet another sort of what I would call specialty equation that you can use whenever you're dealing with projectile motion. Now, bear in mind that this equation is nothing more than combining the equations that you've already seen, so it's nothing new in that sense. You can go through the derivation in your book if you want, but you can just use this equation directly rather than combine equations. This equation will tell you the range of a projectile, in other words, its horizontal displacement, but in the derivation, as you'll see in the book, there is one important assumption, and that is that the vertical distance, there's no height change. So you have to have your projectile returning to the same vertical position from which it started in order to use this equation. If the projectile is shot up onto a cliff or comes from a cliff down below, like the previous example that we did with the person jumping off the cliff, you cannot use this range equation. But for the game of baseball, where things are often coming up and going back down to about the same height, then we can use this range equation quite frequently. So let's take a look at something like that. Let's take the example that you see here where a batter is hitting a ball, and what we're given is the initial speed of the ball as it leaves the bat, along with the angle that that velocity vector makes with the horizontal. And we want to actually know two things in this problem. We want to know what its range is, but we also want to know how long it will take to land. Okay, these are things, by the way, that outfielders may be mentally calculating, even though they're obviously not doing the equations like we are doing. In order to judge where they need to be at a certain time, they have to have some sort of gauge of how far the ball is going to go and how long it's going to take to land. So these are fundamental questions we're trying to answer here. So let's test our condition here. Can we use the range equation even? Well, technically, if this ball lands on the ground, it will be at a slightly lower height than the height at which it was hit. But since that's only going to be about a meter or so, that's close enough that we can approximately take the height change to be 0, and it seems to be a safe use of the range equation. So with that in mind, let's take step 1 and 2 in our procedure, and let's draw a sketch of the situation and define a coordinate system to go along with that. Once we have a picture of what we think the problem entails here, a baseball moving on a trajectory like you see here, and starting at the origin where the hitter is, and taking on this parabolic shape, then we can start to think about what it is that we know and don't know about the problem. I have a feeling, by the way, based on the way I've sketched this here, that this is going to be a home run that was hit. So let's see if we can quantify that and find out if that's the case. So what it is that we know? Well, we know the initial speed. Notice that this says speed. It doesn't tell you the x component or the y component by itself. It just tells you the overall velocity. But we also have an angle, and that's sufficient for us to resolve the velocity vector into its components. We also know what g's value is, and since I've cooked it up to keep the position of the hitter initially here at 0, then when the ball leaves the bat, the initial x position is also going to be 0. Step 4 is to identify what concepts and equations we're going to need. This is a two-dimensional motion problem, unlike the one-dimensional problems that we've seen before, and it involves free fall and projectile motion, and also this new idea here of the range of the projectile. Since we've concluded that we can use the range equation, I'm just going to write it here. And you can see that for the range equation, we don't actually need to resolve that velocity vector into components. That's something we may need to do to find out the time. But for the range equation, we just have the overall velocity that appears here in the equation. So that's nice. I can plug this 37 directly into here, along with the angle theta here. And whenever I do that, I should come up with a range of 134 meters. Seems pretty far, potentially a home run. We shall see. The next step of the problem-solving process is to find the time. We were asked to find how long it will take to land. For this, we're going to take the y equation of motion, and we're going to solve for time because the height change here is going to be equal to 0. We won't actually need to use the quadratic formula in order to solve for this. We can solve for it algebraically, and what we come up with when we do that is a time which is equal to 6.04 seconds. Okay? And so the last step then is to check our answers. We've decided that the range is 134 meters and the time is going to be 6.04 seconds. So do those things make sense? Well, the outfield wall is going to be on average located, depending on the baseball field, at about 121 meters. So 134 meters is definitely outside of that outfield wall, and it would be a home run, but it's not outlandishly far. It makes sense that it's something that a baseball player might be able to hit. The time, well, it might be hard to think about how long it takes to get a ball out there into its full range, but another way you can think about it is if I plug this into the equation for velocity, say velocity in the x direction, for example, the velocity in the x direction would be equal to the overall velocity times cosine of theta. Okay, but we can also think about that in terms of the range being equal, the range divided by the time being equal to the velocity in the x direction. And so if I take this divided by this, I get some initial speed in the x direction of about 22 meters per second, which doesn't seem altogether unreasonable given the overall speed here. And in fact, I can check that by calculating v naught cos theta based on this, and I will find that these two initial velocities in the x direction do agree. So in other words, it meets our sensibility check, and we can be satisfied that we have solved this problem accurately. Okay, so in order to do this problem, we relied upon, for the first part, using this range equation. But the question is, what happens if there is a height difference between the initial and final states, and I cannot make that assumption that y minus y naught equals 0, and therefore I can use the range equation? Am I just stuck? Well, not necessarily. This particular example goes through a different way of solving when you can't use the range equation. As you can see here, this ball that is tossed down is going to land at a different height than where it started, but it's also going to make a horizontal displacement here. This is really just the same as what we had with the person jumping from the cliff. And in fact, we were able to solve that problem given the same sort of given information, and so likewise we can solve for this problem as well. For this ball being tossed out of the window 8 meters high at 10 meters per second and 20 degrees below the horizon, I can summarize all of the known information as you see here, and I can identify that this is a two-dimensional projectile motion problem, and I want to know how far the thing is going, so I'm looking for this x value right here. Okay, and then I'm going to go about solving this problem in the same way that I solved the person jumping off the cliff, where I'm going to use this equation in conjunction with this equation by first solving for how long it takes the ball to hit the ground and then plugging that into the equation in the horizontal direction so that I can find this distance that the ball went. When I do that, I find a time of equal to 0.98 seconds and a distance equal to 9.2 meters. The last step then would be to ask ourselves if that makes sense. So our sensibility check, step 5, is to think whether or not 9.2 meters makes sense. And based upon the example that we had before of the person jumping off the cliff, it's within the same sort of range, and so it's not something that seems too outlandish. It should be something that we can agree is sensible, and so we're satisfied with this result as well. Okay, so this concludes our discussion about 1- and 2-dimensional motion. Next time we will do a brief summary and review of everything that was discussed with these kinematics equations, and then we will start going on to asking ourselves what causes motion, and that's where we will start thinking about forces and how they act on objects. More on that next time.